Hello and welcome everyone to my channel Code with Ease by Varsha. So we are doing a series on time and space complexity in which we cover the introduction and overview of time and space complexity. What are the different common misconceptions related to these, the characteristics of a good algorithm, why do we even need time and space complexity, what sets it apart, comparison of different runtimes like log n log n square and all of that. And then couple of code examples or snippets, and then we are going to deduce live how to get the time and space complexity out of those. So there is an entire plan of the series. So I'm hoping you guys are going to stay tuned, and please don't forget to subscribe to the channel so that you can never miss an update whenever we are posting a new video on this channel. So without further ado, let's begin.
Today is the part 2 of the time and space complexity series that we are doing. In the previous video, we have discussed in depth about time and space complexity, why do we need those, how to analyze the various asymptotic notations and all of that. I would highly recommend you all to first watch that video and then continue with this. So in this video, today's session that we are going to do, we are going to discuss about the various runtimes that exist with examples, with the terms that we are using. Then at the end, we are going to do the comparison of those popular runtimes that we are going to use frequently. So in the previous session, I have discussed about something called the big O notation. This is something very popular when we are learning time and space complexity, the most important asymptotic notation. What is big O notation? This is the maximum time an algorithm takes to execute whatever logic it has to. So the term max is key over here. This is the most important term because it denotes the upper bound or the worst case time complexity. So all of that we have anyway covered in the previous video. What is what? So today's video is going to be an extension of that, because we are going to discuss about the different big O notations or the big O runtimes in detail with examples. So the first one that we are going to discuss about is O of 1. It's usually denoted by like the constant space time complexity. O of 1 or constant space or time complexity. So what is O of 1? When algorithm execution is not based on the input size n, like completely independent of input size n. Classic example, the print statements that we have. Is it dependent on whether you have 10 inputs or 1000 inputs? No. Variable declarations, not dependent on how many inputs you are given to the program. So that is all about O1, order of 1 runtime complexity. The next one is the most important and frequently used, order of n. What it means? Then the algorithm execution, and pay attention over here, increases linearly with respect to the input that we have given. Just draw one demarcation line over here so that you can understand. So it is increasing linearly with respect to input. So if you draw a graph, something like this, okay, it's increasing in a linear fashion. Something like when we have to iterate through all the values in the input. So I have, let's say, 10 inputs or I have 1000 inputs. I have to iterate through all of them. Like example, for loop. So I have a for loop starting from 0 going till n, I plus plus. Within that I am printing the value of I. So essentially I am walking through every value till n, from 0 to n. So I am iterating through all the values in the input. That is why this program is going to run n number of times, and hence the time complexity O of n. It is also called linear time complexity. So these words are important. Okay, moving on. Order of n square. Okay, just as we discussed about this is the linear time complexity, we also have a name for this. We call this the quadratic time complexity. What it means? When the algorithm execution increases, again pay attention, non-linearly. Okay, so as simple as I am having 10 inputs in the previous case, and 10 inputs is taking 1 second. I have 100 inputs, and that is going to take maybe 3 seconds. I have 1000 inputs, and that is going to take, let's say, 5 seconds. So it's a gradual increase, nothing rapid. In case of n square, what happens? The same thing. Let's say initially it's taking 1 second. Now it might take like 10 seconds. And when I'm giving 1000 input, maybe it is taking 500 seconds. There's no correlation. So it is not increasing linearly. Okay, it's like a non-linear increase. So that is the situation with order of n square. Another very good example for this is nested loops. We always come across this, like one for loop within another for loop. The inner for loop is dependent on the outer for loop's value. So if I am running this from I equal to 0 till n, and my inner for loop is having j equal to I, that is also running till n. So for every value of I, my inner for loop is dependent on the outer for loop's value. And based on that, it is going to iterate through every value that I have in the input size. Again and again it is traversing through, because it is dependent on the outer for loop's value. So that kind of a situation happens often, which is obviously not a good time complexity. But for those kind of cases, we have quadratic time complexity. It can be n square. If there are 3 loops, one dependent on another and so on, it can be order of n cube, or it can go even worse. So that kind of a time complexity is called quadratic time complexity, where the execution time is increasing non-linearly. It is also called as polynomial time complexity. Okay, moving on. Order of log n, or big O of log n. This is very important. As important as order of n, because order of n, order of log n are considered good, viable, optimized runtimes. Okay, most of the times we are asked to bring it down to this kind of a runtime. If it is worse, like order of n square kind of a worse situation. So order of log n, what it means, when the algorithm execution decreases the magnitude of input data in each step of computation. It is decreasing the magnitude of data only. Obviously, if it is decreasing the magnitude of the input data, the time it is going to take to run is also going to get reduced. There is a term which is there for O of log n. It is called logarithmic time complexity. So when algorithm execution decreases the magnitude of input data in every step of the comparison, in simpler words, what is actually happening is, let's say I have my input data which is increasing rapidly, like 2 square, 2 cube, 2 to the power 4, like this, but the time that is taken to run this kind of input size, time taken is increasing linearly. Okay, so if I have 10 elements, that 10 elements is taking 1 second. If I have 100 elements, that is taking 2 seconds, not 10 seconds. Okay, if I have 1000 elements, that is taking 3 seconds. So time is increasing linearly, whereas my input size is increasing like exponentially. So my input data is increasing exponentially, but the time taken is increasing linearly. So what is actually happening behind the scenes is, when I'm scaling up my input size from 10 to 100 to 1000, the reason why it is taking linear time to execute is, it is actually not iterating over the entire input data set like we were doing in order of n, where every element of like 0 to n was being touched upon. In case of order of log n, the way to achieve order of log n is when you are not iterating over the entire input. We'll see that with an example. Let's say we talk of binary search or quick sort. These are classic examples which are having log n time complexity. In binary search, what actually happens? I have an array of n integers. Let's say I have 8 elements in this. Okay, so initially my search space, binary search is what, like searching for an element in a given array. Okay, initially my search space is 8 elements. Then I divide the array into half. 4 elements here, 4 elements here. Now I will look in either of them based on my condition. Then I again divide the array in half. 2 elements, 2 elements. Again I look in either of them. Let's say I look into this. Then I am again dividing into this. 1 and 1. That is the base case. So what is happening over here? 8 elements, I started with 8 elements as my input data. 8 by 2, I got 4. Over here 4 by 2, I am getting 2. Over here 2 by 2, I am getting 1. So when I made a point that the magnitude of data is decreasing with every step, this is what is happening. The magnitude of the data started with 8, then came down to 4, then 2, and then 1. And it stopped, because 1 element means we are done. We are doing how many number of iterations? We are actually doing 3 iterations. 1, 2, 3. Okay. So if I have k iterations that is being done to compute for n, 3 iterations to compute for 8 elements, 3 iterations for 8 elements, or what can I represent 8 with? 2 to the power 3. So I can say that 2 to the power k is equal to n, where k is the number of iterations. Here I'm doing 3 iterations. So if I'm doing 3 iterations, or k number of iterations is when I can get to my entire search space of n. So if I take log on both the sides, so here I'm just trying to deduce the time complexity. How we are getting log n complexity. I'm taking log on both the sides. So what happens? K log base 2, here also log n base 2, and eventually the logs cancel and k is equal to log n base 2. Again, just want to remind what is k? The number of iterations. So number of iterations is nothing but the log of the input that we have. So in this case it was 8, log of 8 or log of 2 to the power 3, or which is equal to 3 log 2, or it is equal to 3. So if I have an input of n, the number of iterations that I have to do is essentially boiling down to log of n, which is a smaller value, and hence I am always talking of decrease in magnitude of input data that it is doing, because of which the log n time complexity can be produced. Okay, I hope log n time complexity is crystal clear after this. Moving on to the next one, this is O of n log n. So we discussed about log n, we discussed about n also, order of n. This is n log n. This is called linear rhythmic. So earlier we discussed about linear, that was O of n. Logarithmic, that was O of log n. This is linear rhythmic. It is both a combination of linear and logarithm. So linear rhythmic time complexity. What it means? This is slightly slower than O of n, okay, but better than O of n square. Like not as worse as n square, but it is little bit slower than O of n. So if I have to compare only O of n log n and n, I would say n order of n is a better time complexity. We will anyway at the end see the graph of the comparison of all the runtimes. Okay, so all the sorting algorithms have this time complexity. Like this is the best possible time complexity that they can have. Example is merge sort. I have a playlist on sorting algorithms, so merge sort is also covered over there. If you are not aware of what merge sort is, you can definitely go to the sorting algorithms playlist in the description and check out the video on that. So in merge sort, just a brief overview, I don't want to discuss in detail. Basically it partitions the array in 2 halves, like we were doing in case of binary search. So it will partition in 2 halves, and then it will merge the 2 halves in linear time. Okay, so since it is trying to partition in 2 halves, and as we have seen in the order of log n, whenever we are trying to do some partitioning, automatically I'm getting log n complexity, because I'm reducing the input data size in every step of computation. But when I have to merge those 2 halves in linear time, when I have to merge those 2 halves, it is taking off n. So that combination of n and log n is getting multiplied, and that produces n log n complexity. So the last one is order of 2 to the power n runtime. This is called the exponential time complexity. It is 2 to the power n. What it means? What it means when the algorithm execution doubles in magnitude. Okay, this is important. It is doubling up in the magnitude with each increment to input data set. So this is literally the opposite of the order of log n complexity. There the magnitude was decreasing, here the magnitude is doubling up. A very famous example of this kind of a complexity is the Fibonacci sequence. How does it look? Starts like this: 0, 1, 1 plus 1, 2, 2 plus 1, 3, 2 plus 3, 5, 3 plus 5, 8, and this is the Fibonacci sequence, where every number is a sum of the previous 2 numbers. So if I have to explain that, express that in terms of a function, it is f of n is f of n minus 1 plus f of n minus 2. You can substitute the values of n, you will get the respective value. Like for example, if I have to do f of 2 is nothing but f of 1 plus f of 0. When I say f of 2, I mean the second Fibonacci number, and f of 0 is 0, f of 1 is 1, and f of 2 is this one. 1 plus 0 is giving you 1. Again, if I am doing f of 3, so if I have to denote in terms of a tree kind of a structure, let's say I am doing f of 3. So how can I break it up? will be 2 and 1, like f of 1 and f of 2. F of 2 can be broken down again further into f of 1 and f of 0. So f of 1 and f of 0 are the base cases. We cannot go beyond that because we already know the values of f of 1 is 1, f of 0 is 0. So how many steps this is producing? 1, 2, 3, 4. So f of 3 is producing 4 steps. So if I have to do for f of 4, how can I do it? F of 3, f of 2. Again, this will be broken down into f of 2 and 1, and this will be f of 1 and 0. And this again 2 will be broken into f of 1 and f of 0. So how many number of steps are this? 1, 2, 3, 4, 5, 6, 7, 8. So when I'm doing f of 3, I'm getting 4 steps. When I'm doing f of 4, I'm getting 8 steps, like almost doubling of the number of steps. So when I did f of 2, I had 2 steps, f of 1 and f of 0. When I'm doing f of 3, it's getting 4. F of 4, it is getting 8 steps. So as I'm progressing linearly, my input f of 2, then f of 3 and f of 4, the amount of steps that it has to do to compute the result is increasing exponentially. And that is the reason it is called the exponential time complexity. So just imagine if only till f of 4 it is producing 8 steps, how many steps will it produce if I'm giving it f of 1000? So that is all about all the different runtimes. To give a summary, we first discussed O of 1, then we discussed O of n, then we discussed O of n square, O of log n, O of n log n, and finally O of 2 to the power n. 6 runtimes we discussed. Now let's talk about the graph in which we are going to do the comparison of these runtimes from best case to worst case, like best case time complexity to the worst case. So today's session will be incomplete if we don't do the final comparison of all the runtimes, the important runtimes that we have discussed. So this is a very famous graph of the comparison of the runtimes. Understanding this is important because when you know what is placed at which position, which is better, which is worse, the comparison of this, so that whenever you are asked to optimize your algorithm, you will be able to understand from what to what I have to improve the complexity. Like if I'm having a complexity of order of n square, if I have to make it better, shall I make it order of n log n, or shall I make it order of log n? Which is greater, which is smaller, which is better, which is worse, that kind of a thing. It gives some good clarity when we look at this graph. So as you can see from the color coding, green are good and excellent, yellow is fair, yellow is bad, and then red is horrible. Okay, so starting from the excellent runtime that we have at the bottom, we have order of log n, the logarithmic time complexity, and the constant space O of 1. So both of this, if we are achieved, any of these, if we are achieved in our algorithm, it is good enough. Like the excellent is order of 1, and then one level lower than that is order of log n, because that is in the light green, it is good, and excellent is order of 1. After that, we have the linear time complexity where most of the algorithms fall. Okay. Then we have n log n, the linear rhythmic time complexity, which is worse than order of n, but it is still better than order of n square, like we have seen in the video. Because after n log n, whatever complexities we have, n square, the quadratic, 2 to the power n, the exponential, and the factorial, all three fall in the worst time complexity. So it is always better to have your algorithm's performance in this range, from green to the yellow. It shouldn't exceed beyond the yellow category. So that is a wrap for today's video, where we have discussed in detail about every runtime complexity, and then at the end we are doing and then we have done the comparison of all the runtimes. In the upcoming videos, we will do hands-on, like practically we are going to analyze the time and space complexity for a given code snippet. We are going to do a couple of different types of code snippets to understand how it works in practice. So thank you so much for watching this video.